Okay, so good afternoon. So I've set today's warm-up with specific intent. It pulls from yesterday's warm-up. So I threw down the gauntlet at the end of yesterday's warm-up that I offered bonus points for anyone who would be able to find the answer. No one in this class took me up on that, and I've decided to close that opportunity. And what I'm going to do is I'm going to reveal how to find the answer to yesterday's, and I'm going to throw down a new gauntlet. Now I'm going to offer bonus points to anyone who can tell me the answer to today's. So I'm going to come over here. I'm going to rename this Lesson 10.5 Warm-Up Bonus. And anyone who can offer the answer with an appropriate explanation of how you arrived at it will be accepted. So what I'm going to do is spend a few minutes going over with you how to arrive at the answer to yesterday's. Just to refresh your memory, yesterday's warm-up, the warm-up for 10.5 asked for the radius of the circle. So, let's get the answer first. Alicia, what is the radius of the circle?
10.
The radius of the circle is 10. So, you needed that piece of information to proceed with today's. But we're not going to talk about how to proceed. We're going to talk backwards and go, how do we get the 10? So what I want you to do is focus on something particular. I drew this radius very intentionally, as opposed to drawing a radius here or over here. Because when I draw this radius, I get something. What do we get? Dalton? We get a right triangle. So you should be, at the moment, with me on your, I gave you that special cheat sheet for today, and you've got this now that you're looking at. However, we're missing a lot, so let's fill in what we know. We actually know the distance from X to A. What is the distance from X to A? Davis?
6.
It is 6. Can you prove it, though? Why is it 6? Go ahead.
Because the total distance from A to B is 12, and since it's the chord, this is a chord, and the other one's a diameter and a perpendicular, it cuts it right in half.
Very good. That was a great explanation. This is a chord. This is a diameter. A diameter will always cut a chord in half. It's a perpendicular bisector. 1 second. So we now know that this is a right triangle and that is 6 because the whole distance was 12. So your mind should be kind of reeling at this point. It's like, I know what I could do with right triangles, but how do I get everything I need? Okay? So, Dalton, you have a technique for getting what we need? What did you do?
OA is common to OC.
That is correct. OA is a radius and so is OC.
Yeah, and it says that X to C is 2.
Very good.
So OA minus 2 equals X to O.
That's right. So, there's 2 ways to represent it. I'm going to do it a tiny bit different than what he said because I realized after watching one of your peers do it, it was a little bit better. We don't know this distance right here, but we do know the 2. So let us label this distance x. I shouldn't use an x because of that, but I'll use an x just for argument's sake. So that distance is going to be x. This distance is 6. This is 2. Dalton very wisely said AO and CO are congruent, which means AO must be x plus 2. Pythagorean theorem. 6 squared plus x squared must be x plus 2 squared. 6 squared plus x squared must equal x plus 2 squared. Dalton did it almost the same way. He represented this as x minus 2 and that x. It's basically the same thing, just written the opposite way. So you solve that, and you get x equals 8. Therefore, the radius is 10. This radius is 10. Okay, Feng, I apologize. You've been waiting patiently. You had something to contribute or something different? Go ahead. Go.
So I drew a chord from A to C.
Yep.
Then I did a Pythagorean theorem, which I got 7.
Okay.
So
I'm going to do it over here, but I know exactly what you're saying. So you drew basically this distance here, and then you knew that was 2 and that was 6, so you did Pythagorean theorem, you got that orange distance as 7. Beautiful.
And then I don't remember what it's called, but I think it was a scale factor.
Okay?
So I did 2 over 7, which is equal to 6 over x. Then I solved it, in which I got x is 21, which is the hypotenuse for A to D, which also B to D, and then I did a Pythagorean theorem again, which I got 20, and since the radius, I got 10.
Well, I'm not sure because you made an assumption. The only way you can do a ratio between this triangle and this one is if they are similar triangles. And the question is, are they? Are they? Let me draw the orange line up here. And Zabari, I see you. Just give me a moment. Are they similar triangles? The only way we could say for certain, just by looking at it, that they're similar is if this is a right angle, and we do not know if that's a right angle. So it's possible to get the right answer, and it's possible you got lucky with some of it, but I would have to check. So I'm going to look at what you did, and I'm going to go through it myself and see if it's a valid approach. Okay? Zabari, you've been waiting patiently as well. Go.
I didn't do anything with radius. I drew a chord from A to D and a chord from A to C and C to D.
Okay. So you took this approach. Yes, I remember you describing to me. So you did this, and then you did something similar to her, here and here. Good.
And so since triangle DCB lies on the diameter, I knew that angle B has to be right, and angle A has to also be right.
Very good.
And so I did the Pythagorean theorem with triangle AXB to find out A to C, and since that's also congruent to C to B. So I figured out that if the ABC was a kite,
ACBD is a kite. Yep.
yeah, and so what I did was I figured out I used the tangent for 6 over 2, the inverse of tangent to find out the angle of angle C.
Very good.
And then I just added up to find the angle B.
Very good. That was great that you figured out, because of the way you drew this, that was a right angle and that was a right angle. So you knew that 90 and 90 was 180. You figured out that, and then you subtracted all of that from 360 to get that whole angle. Good. So does that mean that you figured out the measure of angle CDB? Okay, very good. So I'll put you on my list, but let me check, and please don't tell anyone what the answer is. It's a great approach. As I said, back to when Brian asked, is there a way to do this without knowing the answer to yesterday? Well, I think he's right, and there's a way to do it without knowing the answer to yesterday. As I've said over and over again, you guys see things that I cannot possibly see because you are blessed with more gifts and more brain power than I could ever hope to have. So I will never say that this is the only way to do it. That would be just unbelievably foolish. So we've seen a lot of different perspectives. Are there any comments, questions, any observations at this point? All right. Okay, we are back as a whole group. Today is lesson 10.5. We're going to be exploring angle relationships in circles. You would actually, if you reflect back, just maybe a week ago, you guys knew very little about circles. And we have, at this point, attained an incredible amount of knowledge about circles and lines that intersect, circles and angles that arise from those intersections, chords, tangents, a lot of different ideas floating around about circles. And you've got a lot of tools in your toolbox to solve problems involving circles. We're going to add to that today. Some of the tools that we're going to learn today are complicated. Another challenge from today is that some of them seem similar to each other, and it might be easy to get them confused. So keeping things straight is going to be a little bit of a challenge, and the complexity of the ideas is going to be a little bit of a challenge. So our goals by the end of today are to be able to find the measures of angles formed by lines that intersect with circles, and to use these angle measurements to solve problems. I'm going to bounce back and forth between kind of moderate and easy, moderate questions to more challenging questions. We're going to go back and forth today. You have at your desk a copy of every diagram that's going to be used today. I did that on purpose because I felt like they were too complex to ask you to draw them out. There was a lot of them. And I wanted you to be able to add in details as you work through the problems. That's actually a key piece, is to be able to look at something and just start adding in things that you already know about the diagram in an attempt to try and work through what I'm asking you to do. So let's go ahead and look at the theorems that are involved today. There are three major ideas. The first, it's called the tangent chord angle theorem. It doesn't really matter what the name is. What it says is, if you have a chord intersecting a tangent line at the point of tangency, that the measure of the angle formed will be half the measure of the arc that it's intersecting. So, what we're looking at is, we are looking at this angle here and here, formed by those two segments. And then we're looking at the relationship that that has with this arc right here. The angle will be half the measure of the arc. Conversely, the arc will be double the measure of the angle. If we were to look at the other side, angle 2, or the angle formed by this and this, this angle's measurement would be half the measure of this arc. The arc is formed by the vertex and the end point of the chord. So that's a tool to add to your vast toolbox, and we're going to use this quite a bit today. Any questions about that? In and of itself, not too hard. But when I throw in this, then all of a sudden things start getting jumbled around and a little confused. So that's where I was saying keeping things straight is a little bit of a challenge. Angles inside a circle theorem. If you have two chords intersecting, the vertical angles formed, each of those vertical angles will be half the sum of the intersecting arcs. So that was a mouthful. We're talking about the relationship of this angle here and the arc formed here and here. This angle will be half the sum of these two arcs. This angle, angle 2, formed here, will be half the sum of this arc and that arc. Any questions?
So the angle and the vertical angle to angle 1, would that be the same thing?
That's right. Because this angle is the same as this one right here, that can be found using the same technique. It doesn't matter which one you do, they're both the same. This angle is another instance of angle 1. So that angle will also be half the sum of that arc and that arc. Very good point. Lastly, we will explore angles outside the circle theorem. And it looks a bit intimidating, but it's not as bad as it looks. We have 3 different cases. We have 2 tangents, 2 secants, or a tangent and a secant. And they're forming an angle outside of the circle. So we're talking about these angles formed out here. There is actually a relationship between the measurement of these angles and the arcs that they are intercepting. The measure of the angle will actually be half the difference of the 2 arcs. Difference meaning you subtract them. So the measure of this angle will be half the difference of this arc, and you always start with the bigger arc and subtract the smaller arc. This angle will be half the difference, bigger arc, smaller arc. Same thing here, half the difference. So if the lines intersect inside the circle, and you're talking about angles in the circle, you add the arc measurements and then divide by 2 or take half of it. If the segments intersect outside of the circle, then the angle formed will be the result of half of the difference of the 2 arcs. So it is a bit involved now when you throw everything all together. Okay? So we're going to jump in and get to work. So everyone find the first diagram for examples. I didn't number them or anything, so you're just going to have to just look and know which one we're using. And we are going to start out a little bit simpler and move to moderate. So let's start out with simple. Find the measure of angle EFH. So EFH is formed by these 2, that ray and that segment, that tangent and that chord. And so the theorem, the tangent chord angle theorem, says that that angle will be half the measure of this arc. So that's pretty simple. What will the measure of the angle be? Sebastian? 65 degrees. So there was nothing complex there. It was just straight use of the theorem. The measure of the angle will be half the measure of the arc. Any questions about that? Okay, part B. I would like us to find the measure of arc GF. So, separate question, so let me get rid of this. So now I would like the measure of GF. So I'd like to find the measure of that arc. You got it already? I'll get to you in a second. That arc has a relationship with this angle that's formed here and here. But we don't have that angle. And we don't have the arc. So Catalina, what did you see?
I saw that it's a linear parallel to an angle at the
Yeah, there's no letter over there, that's fine. So we can use the idea of linear pair supplementary angles to find this angle. So what is that angle? Okay, go ahead, Dalton, you got it? Okay, so this is 58 degrees. That's the measure of the angle that I've highlighted in green. And then multiply that by 2 and you will get the measure of the arc. And it comes out to what? 116 degrees. Any questions about how to use the tangent chord angle theorem? Brandon? Comments, questions? Okay. Checkpoint number 1 is going to use the diagram that comes next. So find the right diagram. And find me the measure of arc RT. And find me the measure of angle RST. You got 2 questions. You got 3 minutes. Yeah. Don't tell anybody. All right, let's see how we're doing with the tangent chord angle theorem. Stay on your toes. Equity bars in effect. Part A only. What is the measure of arc RT? I've got student 13, 2, and 21. Okay, student number 2? Student 21? So the measure of arc RT is 52 degrees. So I know 3 students got it right. We'll see how everyone else did. And then part B, what's the measure of angle RST? I got student 24, 14, and 20. Student number 24. Student 14. Student number 20. So I've got 3 students who agree that it is 26, and it is. Give me a thumbs up if you got both of them correct. Put your thumbs down. Question? Yeah. Part B? You got part A? So you got that this arc was 52 degrees.
Oh.
This angle will be half of that angle. That's okay. It's a simple memory lapse, no big deal. All right. Now, angles inside the circle theorem. As we talked about earlier, 2 intersecting chords form angles. The angle measurements will be half the sum of the intersected arcs. So, let's see how this plays out. Find the measure of angle AED. So, I am looking for the measure of this angle. And the angles inside a circle theorem says that there's a relationship between this angle and the 2 intercepted arcs. However, we don't have the angle and we don't have the arcs. But what do we have? What do we have that we can use? Alicia? Okay. Well, so go ahead, name them for me. Very good. So we have these arcs. And so we could find the measure of this angle using those 2 arcs. And then what could we use once we found the blue highlighted angle? What could we do to find the yellow? Once we find the blue one, right? Yeah, it's just a linear pair. So let's use the angles inside a circle theorem. Bless you. So the measure of angle AEB will be equal to half of the sum of the intercepted arcs, 139 and 113. So what is the measure of angle AEB? Anyone already got it? Got 1, 2 people who already got it? Give people a chance to do the computation. Tristan, what does it come out to?
54 degrees.
Comes out to 54, is that correct, Caleb? Angle AEB, this blue angle.
Oh, I did the wrong one.
You got what? You got 126, so we got 54, 126. Which one is it? What did you get, Jada? Oh, it's 126, I'm sorry. So this is 126, and then according to Brian, this is a linear pair, so we can just simply subtract and get the other one, and Tristan, the other one is?
54 degrees.
So the measure of angle AED is 54 degrees, and that's what we were looking for. Any questions on how we approach that? Any questions on how to use this new tool, this angles inside a circle theorem? Go ahead.
I have a question.
Or comment, anything at all.
Well, I just found angle AED, multiplied it by 2, and subtracted from 360, and the difference I divided by 2.
Hold on. The angle AEB you got by doing what?
By doing that, and then I just multiplied 126 times 2, and I subtracted that from 360, and the difference I divided by 2.
Okay. So because this and this are vertical, so they're going to be the same, and then this and this were going to be vertical, they're going to be the same. So you knew that once you had the total amount for the yellow ones divided by 2, you get one of them. Which method is more efficient? Okay. Good. Any other comments or questions? And just so you know, Ann, you're not the only person who told me that they did that. Good. Checkpoint number 2. Find the diagram on your paper and find me the measure of arc YZ. This is a higher level question, so I'm going to put 6 minutes on the clock. I would like you to work independently for at least 2 minutes of that on your own. You may engage in dialogue with your teammates if you feel like it will help you after 2 minutes. So please work independently to start. Of course, you can ask me anything you'd like, any guidance you need. Yeah, I'm sorry. XY is a tangent line. I should have said that, but I guess I eliminated that detail. But yeah, XY is a tangent line. Yeah, sum. That'll. Don't tell anybody. Got 1 minute. Yes. What you added is all right. Now, this is the type of question that I would rather everyone have a chance to get it right. However, I am going to reveal the answer, and we are going to go over this one so that you can start seeing the level of thought involved in working through a more complex situation and how you can use all the tools that you're learning and tools from the past to get you what you need. So first, let's get the answer, and I know there's a lot of people out there who figured it out. So I'll start with some random names, and then if that doesn't work, then you guys will chime in with who got it right. Student 13, 10, and 4. Student number 13, what'd you get?
I got 112, but that's definitely not the answer.
Okay, student number 10. Okay, student number 4.
I got 164.
164 degrees is correct. 164 degrees is correct. So I know of 1, 2, 3, and give me a thumbs up if you got it right. 1, 2, 3, 4, 5. Good. So I'm going to be calling on all of you. Put your thumbs down. Jada, thinking back to when you found the right path, what was the first step in that path? Take a moment to think back. What was the first thing you figured out?
I think I did we made it 68 divided by 2 to get angle V, W, V, Z, and then use that.
You didn't do 68 divided by 2 to do that. That wouldn't work. You did something else. You did something else. So you're having trouble
Oh,
remembering.
I know what I did. I did X, Y, Z, that angle, and I used, wait, I can't remember now.
Okay, that's okay. That's fair. Catalina?
I did 180 minus 150.
Yeah. This right here. The whole key is this triangle right there. 180 minus 113, you get 67 degrees right there. However, that doesn't really get us anything. We're looking for this arc over here. I'm looking for all of that measurement right there. That doesn't get us anything. But if we can find the other part of the circle, then we could subtract it from 360 to get this, and we already have the 68. So if we can get this arc right here, YUW, that arc, we can add it to 368, subtract it from 360, and get this. To get this arc, we need this angle right here. And we're very close. So Brian, how do we get that angle?
I did not do that, but you subtract 49 and 67 from 180.
That's right. And so what does this angle come out to? Oh, you did it differently. I'm sorry. It comes out to 64. I apologize. I didn't mean to put you on the spot like that. So once you get that as 64, now you can find the measure of this arc right there. What is the measure of that arc? David? You did it differently as well? Okay. Well, you should be able to do it right now because you just learned the theorem that explains the relationship between that and the arc. So what's the measure of the orange arc that I just drew? Jada? It's 128. Double this is going to give you the arc. So now we have 128 and 68, and that's that part of the circle, and we're looking for the other part of the circle. 360 minus 128 minus 68 equals 164 degrees. So you really had to think about what you needed, what you had available, and how to kind of incorporate different ideas and tools that you have at your disposal. That's why, and Zabari was very good to point out that I didn't put it in the text of the question. That's why it was important to know that xy was a tangent, because of that relationship between the tangent and the chord. Okay? So Brian, and Davis, I want to hear what you did, but I have to conserve my time. So I'm going to come over to you at the next chance I have so you can show me what you did, and then I will give an opportunity to share out at some point. Okay? Any quick questions on this? Again, keep in mind, this was supposed to be higher level. All right, so now we're going to continue with high level stuff. Angles outside the circle theorem. If you have angles outside the circle, the relationship is that the angle measurement will be half the difference of the intercepted arcs. So we already spoke about that, so let's see how this tool can be useful in a complex situation. So find the picture on your sheet that looks like this. Read the text of the question to yourself. So we are supposing that a flash of northern lights goes off right at that point. And I would like us to find the measure of this arc, which represents the people on Earth who can see that. And do a very good job drawing that. Let me try that again. Those are the people who can see it. If you live right here, you won't be able to see it because the angle just won't allow it. Clearly, if you live over here, you won't be able to see it either. So that's the angle, the arc, representing the people who can see that flash. So the angles outside a circle theorem says that there's a relationship between this angle right here, if this is tangent and this is tangent, which they are, this angle and this arc and this arc. So we can write that relationship out. The measure of angle C is going to equal half the difference of this larger arc, BED, minus the measure of arc BD, which is the one we're looking for. So we established this relationship, this equation, using this new tool, the angles outside a circle theorem. And our goal is to find the measure of BD. Our goal is to find this. So we need, that's going to be a variable. We need everything else. So we can just call this is going to be x degrees. That's going to be x. So this is going to be x. But that means that we need the measure of angle C, and we need the measure of arc BED to be able to find the missing angle? Let's start with the measure of angle C. What can we do to find the measure of angle C? What could you tell us about that triangle that I just highlighted in green? What could you tell us, Maria? Are you sure? Which one is?
CD.
Is tangent. Okay.
That would make what I forgot what it's called to make it right.
Okay, well, something else has to be true for it to be a right angle. So I'll say this. You are correct. It is a right angle. So that's a right angle right there, but I need to know why. Why, Dalton? It's what?
No, it's a square.
But you've got circular logic. You're saying it's a right angle because it's a square, and it's a square because it's a right angle. The right angle wasn't in there before. I just put it in. So we need some proof. Brandon?
I'm pretty sure that A is the center, right? Yeah, so CD is a tangent and AD is a radius. I believe there's a theorem that says there's always a right angle formed where the radius intersects the tangent.
Yeah, so I neglected and I eliminated from the text of the question because the text was going on and on and on, the fact that AD is a radius. And it is. So you weren't supposed to assume it, I was supposed to tell you it, but it was good that you figured that out. So AD is a radius, that's a tangent and a radius will always form a right angle. You learned that at the beginning of chapter 10. So now we have the measure of AD, it's 4,000 miles. And we have the measure of AC, it's 4,150 miles. Can we get this angle right here? Could we get that angle right in there with the information we have? How? How could we do that? Dalton? Yeah, we could use a trig function, a trigonometric ratio. This is a right triangle that immediately allows the use of trig functions. And so this angle has this as its opposite and that as its hypotenuse. Which trig function works with opposite and hypotenuse? Go ahead, say it in your head. Don't say it out loud, say it in your head and tell me which trig function. Alicia? Sine. So, we can find this angle by doing the sine, and we'll just temporarily call that angle x. The sine of x is going to be the opposite, 4,000, over the hypotenuse, 4,150. Now, we don't use the sine function on the calculator. We need to use the inverse sine. We use the sine when we have the angle. We use the inverse sine when we have the results. And this new calculator doesn't work the same as the old one that we were using. This calculator, you can't use parentheses. So you're going to have to do the division first, then do the inverse sine. So let's get practice with that right now because this is something you're going to have to do. Yes? You already got it? Okay, so just hold on. So I don't have an emulator for this, so I cannot show you what this looks like. So it's going to be 4,000 divided by 4,150. Leave that number in your calculator. Push the bright green second function, and then push the sine button, and you will get the measure of that angle rounded to something nice and appropriate. So Alicia, what does the angle come out to? Comes out to approximately 74.5 degrees. But that's just this. How do we get the measure of angle C from there? What can we do to get the measure of angle C? All of a sudden the crickets invaded. Michaela?
Multiplied by 2.
Yeah, multiply it by 2. So we will get that the measure of angle C is 149. So now we are at this. We are at 149 equals 1/2 the measure of arc BED minus the measure of arc BD. Unfortunately, we don't have any other measurements. So now we have to do some creative thinking, and here's where I'm not asking you to just team talk it. I think some of you might be able to figure it out, but in the interest of time, we're going to work together. I earlier called this arc X. From here to here, we're going to call X degrees, which leaves the other part of the circle as the other arc. How many arcs total are there that we're dealing with? Hold up the number of fingers of the total number of arcs that we're dealing with. How many arcs are we dealing with? Okay. I see a lot of people holding up 3. What are the 3 arcs? What are the 3 arcs? Caleb? I don't know, what? You said BED, that's 1 arc. Okay, well you said one of them. This is 1 arc. Arc BED, that's 1 arc. Some of you are saying there's 3 arcs, so there's 1. Now I need the other 2. What are the other 2, Alicia? Yeah, go ahead. And? Well, but BE was included in BED, so that's not another arc. This is the other arc. We've got 2 of them. Try to stick with me. I know it's been a long, tiring process, but you guys are close. So this arc is 1, and then the red is the other. There's 2 arcs. There's 2 arcs. So the question is, the 2 arcs, if this one is X, what could we call this one? If this one is X, which I didn't write very well, if that one is X, what could we call the one I drew in orange? Chris?
360 minus X.
360 minus X. This one has to be 360 minus X because that one's X. Whatever value we figure out for this, to get this value, we do 360 minus the X. So now we actually have everything we need to fill in. This is going to be 149 equals 1/2 times, now measure of arc BED is actually going to be 360 minus X. And then we're going to subtract from it the measure of arc BD, which is X. Solve the equation. So I know that seemed like it was a lot to get to that, and it was a little bit, but you got to use everything in your toolbox. You got to have everything available. So go ahead, you guys are on your own now to solve that equation. You find the value of X, and you will find the measure of that arc. Yes. So what do you get? Oh, it shouldn't take this long. Come on. Solving a simple equation? I know, the 1/2 is awful. Sebastian, what does it come out to? What is it? What did you get, Brandon?
31.
We both agree it's 31?
Yeah.
Yeah.
You sure?
Yeah.
We have other people who agree that's 31? Oh, yeah, it's 31. 31 degrees. So the 31 degrees would be able to see the northern lights if it happened 150 miles directly above the earth at that point. Comments, questions? Yes, 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 yes. Go.
What if you're like right beside that donut?
You won't be able to see it.
What? So if you're like
Okay, Dalton?
I did it another way. And for angle A, I did cosine, and I multiplied it by 2, and then I got arcade.
That was pretty smart.
I did the same thing.
Same.
Same idea.
That was pretty smart. Didn't even consider that. Zabar, you going to say the same thing?
Yeah.
Oh, that's pretty brilliant. Oh, maybe I'll learn that for next time.
Is it 31 degrees like in a whole circle? 31 degrees?
31 degrees, yeah.
Like not just that way, but this way and that way?
So you're talking about a sphere?
Yeah.
I would assume so. I would have to look. I would have to model it to get a better sense. But yeah, I think you're right. Okay, so I have a checkpoint that's more exclusive for this, but I actually want to skip it because I'd rather get to the team challenge. So we are going to skip over this diagram that's on the back of your paper, and you are going to go to this. Checkpoint number 4 is a team challenge. You have the diagram on your paper. Read the text of the question. Find me the answer. It is a team challenge. If you finish answering the question, then you work on the extension. You've got 8 minutes on the clock. Any guidance or help you need, let me know and I will come help. The diagram's right in front of you.
Hey, Mr. Brown, you know another one of these? Yeah.
Yeah. I don't.
That's true.
I feel like it's last block because I don't know if anybody
Lost?
That's true. So what helps us get from electrons to Burr. Okay, so we are back as a whole group. Back as a whole group. So, we're going to call on a few teams. Let's see what we got for today's team challenge. Team B, D, and G. Team B, what did you get for today's team challenge? Ann. Team D, what did you guys get for the team? And team G, what did you guys get? So the correct answer is 30 degrees. Give me a thumbs up if you and your team was able to get the 30 degrees. Okay, so I got all the teams over there. Oh, I got everybody. Good. So no time spent on that. Good. What about the extension? Give me a thumbs up if you found the radius of the Ferris wheel. Thumbs up if you found the radius. Okay, give me a thumbs up if you attempted to find the radius. Okay, put your thumbs down. Good for you. So, I actually tried. I gave myself a challenge. I think there should be a way to do it, but I can't quite figure it out. So, I'm pretty sure you could figure out some ratios of things, but you could not figure out the exact measurement because we don't have any measurements at all. And I have to wrap up, so I'll get to your questions or comments in a moment. So, you guys did a good job today. Your homework is page 675. You're doing numbers 7 through 13, 16 through 18, 20, 21, and 25. Those are in bold, which means they are going to require extra attention. Do the at-home tutor for 10.6 or read the next section. And you have a quiz on 10.1 to 10.4 tomorrow. So today's lesson will not be included.